Uh, Good morning, everyone. Can you guys confirm if you guys are hearing me clearly? Okay, I want to welcome everyone to my lecture today. Today, February 1, 2021. I'm actually going to be walking you through another exciting topic in statistics. And of course, the focus today is actually going to be on linear regression assumptions. But you know what? How do we get here? Okay, I would like to go retrospective right now. Before now, I introduce you to linear regression. When do we need linear regression? Of course, we use linear regression when we're trying to characterize relationship between two variables in such a way that we actually want to predict one variable from the other one. Okay, and you know what? I introduced you to the model last week. And I remember I walk you through an example on how you can estimate parameters in the simple linear regression model. But you know what? The focus today is actually going to be on the assumptions. I told you every statistical model has assumptions, and assumptions centered on the error. Okay. Now, the focus today is actually to walk you through, you know, the assumptions underlying the use of linear regression model. Okay, before I go ahead, I also want to use this opportunity to tell you that the lecture slide for this week and the lecture slide for next week have already been uploaded. All what I need from you just to check the module. Okay, you're gonna see that. Okay, now I wanted to take no. I wanted to take today. I'm actually going to use an example. If you take a look at the picture that you are seeing right now, of course, this is the former President Trump, and this is Senator Romy. Okay, so the example today, I want to take the example from, politics to tell you that we also apply linear regression in politics. Okay, the example we did last week was actually probably on business, okay, but now we want to apply that in politics. Now, we want to study relationship between presidential election results of 2012 and 2016. And we're focusing on Republican candidates. I'm going to say that again. In the United States of America, there was presidential election in 2012 and 2016. And to the best of my knowledge, in 2012, Senator Roney happens to be the Republican presidential candidate. In 2016, of course, was former President Trump. Okay. Now, what is the focus today? The focus is actually going to be we want to study relationship between the percentage of voters that voted for Republican candidates in 2012, okay, and uh, in 2016. If you take a look at that, if you take a look at this guy now, we're using X. Okay. 2012 actually happened before 2016, right? And of course, in the English alphabet, you're gonna first come across X before we come across Y, right? Now take a look at this. X is actually the percentage of voters that voted for the Republican candidates in 2012. And of course, the Republican candidate in 2012 was Senator Romy, which is this guy here. He's still a senator in the US Congress. Okay. And Y represent the percentage of voters that voted for the Republican candidate in 2016. Okay. Now take a look at that. Now, Now, what is the essence of this? The essence of this is that if I understand relationship between uh, the percentage of voters that voted for Republican candidate in 2012 and and the percentage of voters that voted for Republican candidate in 2016, there's possibility that we can actually use a model to predict if you're given, if you consider a particular county in the United States of America, okay, if a Republican candidate receive a certain percentage of vote in 2012, can we have a way to predict what the Republican candidate is actually going to have in 2016? That is a motive. That is a reason, okay, why we study relationship in linear regression. We study relationship in linear regression just because we actually want to predict one from the other. Okay, now this is a map of United States of America. And you know what? Uh, the observational unit, remember the other time I talked about observational unit, right? Observational units could be cases, observational unit could be persons, but right now, our observational unit is actually going to be county. Okay, it's going to be county in the United States of America. There's so many county, okay? That's going to be the observational unit, okay? Now, let me tell you this. If you take a look at this is looking to me like Alaska, right? Okay, we in this study, we actually want to build population regression model. You know, we're gonna use all counties in the United States of America except the one in Alaska. I'm gonna say that again. We want to build a linear regression model, and it's actually going to be a population linear regression model because we are using virtually all county in the United States of America. We know the one that is excluded is a county in Alaska. Take a look at that, and that is why we call that a population model. Okay, now I want you to pay attention right now because I'm actually going to be talking about some symbol. Now take a look at this. What do we mean by that? That's a population regression model. What do we mean by population regression model? Okay, it means the expected value of y given x equal to beta naught plus beta 1 x. What am I trying to talk about? The expected number of votes received by Republican candidate in 2016, given that a particular Republican candidate in 2012 has a particular value, is actually equal to beta naught plus the beta 1 x. I'm going to say that again. Don't forget, Y represent the percentage of voters that voted for Republican candidate in 2016, which happens to be President Trump. And of course, X represent the percentage of voters who voted for Republican candidates in 2012, which happens to be Senator Romney. Therefore, if you take a look at the small x right here, it's just a particular value. If I know the percentage that voted for Romy in 2012, can I say on average the percentage that will vote for President Trump? That's what I mean by expectation of y given the x equal to small x, and that is equal to the beta naught plus beta 1 x. Now what I'm trying to say right here is that the moment I know my beta naught, the moment I know my beta 1, what I'm actually going to do is to plug in the values of x into that equation, and automatically I will be able to determine on average, the percentage that actually voted for President Trump, which means if I want to know the percentage voted for President Trump, then I can only determine that if I know the percentage that voted for Romy. Okay, Romy was a presidential candidate of Republican Party in 2012, and President Trump was actually the presidential candidate of the Republican Party in 2016. Are you guys still hearing me? Okay, if you are not in my party, if you are not enjoying my party, please let me know. This is not a lecture. This is a statistical party. Okay, now you remember last week that I said if you want to study relationship between variables, you actually need to start by scatter diagram, by you need to start by plotting, right? Now take a look at what I have right here. This is take a look at this. The percentage of voters that voted for Republican candidates in 2016, we are plotting that against the percentage of voters that actually voted for Republican candidate in 2012 across county in the United States of America. Now take a look at what I have right now. This is actually, I have it, we got a lot of scatter points. If you take a look at the the dotted black line, I mean the black dot, that's actually represented, the scatter point. Okay, of course the line of equal distribution is actually the blue line. Okay, take a look at that. And you know what, the beta, this is the values for the beta knots. Okay, and this is the value for the beta one. And let me tell you this, the observational unit is a county in the United States of America, except the one in Alaska. Of course, except the one in Alaska. This is not a fitted model. It is not a fitted model because we did not, this is more or less like the population, virtually all county in the United States of America, except the one in Alaska. And therefore, we're not going to call this a fitted one, model. We're actually going to call this a population regression model because we use virtually all county in the United States of America. Okay, take a look at that. Now, um, based on what we have right here, okay, do you know that based on this, we can actually predict. Now, if 50% of the voters in a county voted for a Republican in 2012, what percentage of voters from the county, I'm referring to that particular county, okay, will vote for a Republican in 2016? Now, you know that using the model right here, all what you just need to do is just to plug in 50% into where you have X, okay? And if you want to do that, another thing you can do, you can make use of the diagram right here. Look at that. Oh my God, this is 50 now. Project that, and project it to this side to be able to.
Have a good one.
Um, I think I want our student to mute. You can only unmute when you want to ask question because of the background noise. Okay. Otherwise, I'm going to mute everyone. So mute right now. Thank you for that. Okay, now take a look at that. I can actually, if I want to determine the percentage that we actually vote for Republican candidate in 2016, I will know the percentage that voted for the Republican candidate in 2012 in a particular county. Okay, I can use the graph. I can use the scatter diagram right now to figure that out. I can also use the model. Take a look at that. Okay, so that is why, give me 1 second, and that's exactly what I'm trying to do. We look at that with the red dotted line. I'm placing that on 50 because they mentioned 50%. And of course, take a look at that, okay? Now, and then another way to do that, like I said, you can plug in 50. The 50 is actually representing X right now. When I plug in 50, now take a look at that. Now, what I'm trying to talk about right now, how can I interpret what I have right here? Now, the interpretation of this guy here is that 53.924% of the voters in that county is expected to vote for Trump. Okay, how do I know this? If 50% actually voted for Romney in 2012, which happens to be the Republican presidential candidate, we expect, okay, look at the word expected, we expect that the Republican candidate in 2016, which happens to be the former President Trump, we actually received 53.924% in that county. Or that county could be NP County, it could be county in Texas, it could be county in California, it could be county in wherever, but you know what? We are excluding county from Alaska. Okay, now take a look at that. And now I want you to see what is the difference between this guy here and this guy here. Oh my God, I want you to pay attention right now. That is where I'm going. There's a difference between average. This guy here is an average. Anytime you see expectation, look at here. The he here means expectation. Okay, we just like the expected value of y given that x equal to 50. It is quite different from y given x equal to 50. Y given x equal to 50 is not an average, but expected value of y given x equal to 50 is an average. Did you get that? And that is what we want to focus on right now. Okay, we're still going to focus on, what is the expected, what is y given that x equal to 50. I'm still going to tell you, okay, which we call individual prediction. Okay, this is individual prediction. This is average prediction. Okay, I'm still going to walk you through that in the subsequent lecture. Okay, but right now, my focus is actually on this. Now, if I told you today we're actually going to go into assumptions, right? And assumptions revolve around errors. Now, the question now is, let us first, let's see whether we can observe there's any error here. Now, when you take a look at this graph, you're actually going to see we get some dotted black, I'm going to get some black dot that are deviated away from the line of equal distribution. Okay, the fact that all the dotted black dots are not on the straight line means there's an error. I'm going to say that again. Let me tell you this, we expect a linear regression to be perfect model. It is the only condition for it to be perfect is when all the points landed on the straight line. But right now, since there's no perfect model anywhere in the world, and every statistical model has a random component, the fact that it has a random component means there's always going to be an error. Okay, and that is the reason why you got some points that are deviated away from the straight line. Are you guys hearing me clearly?
Yeah, boss.
Okay, good job, good job. Now, and that is the reason why I said most observation do not land on the population regression model, and that is the errors that I'm talking about. The fact that they did not land on everyone, did not land on the straight line, the blue solid line. That is the beginning of errors. Okay, but you know what? Most of the dotted line, they are very close. If you take a look at that, they are very close to that. And that actually means the error here is very, very negligible. Okay, for those observations not on the regression line, this is a beginning. If you take a look at this is a question. This can be multiple choice question in the midterm one. I want you to focus on this. You have to choose more or fewer. Now take a look at this. Dash of them are close to the population regression line. Okay? Which one is going to be your answer? Is going to be more or fewer based on what you are seeing right here? It's actually going to be more. Okay? More of them are close to the population regression line. Okay, now if you want, how many of them are far away? We're talking about the one that are far away. Take a look at this guy here. All these ones, they are far away. And there are few of them that are far away. And that was why I said fewer. Okay, here you're going to choose fewer. Here you're going to choose more. Okay, so fewer of them are far away from the population regression line. Oh my God, we are okay with that. We don't expect every dotted line line, but you know what we are actually looking for, we expect most for our regression model to be fantastic, for our regression model to do a great job. We expect most of the point to be very close to the line of equal distribution, and that's exactly what we're seeing right here. We expect the fewer to be far away, which is good. That is what we're looking for. Okay, so that's what we mean by that. And you know what? For each observation, I'm actually going to have that regression model. Okay, this is where we are going. Let us now look at the assumptions. Okay, we also call it conditions. Assumptions are called conditions. Okay, assumption for simple linear regression model, or what I'm trying to talk about, for simple linear regression model to be fantastic, to be valid, we need to be able to, investigate whether the assumptions are violated or not. Okay, and what are these assumptions? Because we need to know this assumption before we can actually know whether they are violated or not. Okay, and you know what? Oh my God, take a look at this right now. Assumption for linear regression are based on the errors. I think I told you last week. Assumptions of linear regression are based on the errors. Okay, so, and these assumptions actually affect the properties of the estimators of the intercept and the estimator of the slope. Take a look at that. You remember I told you last week, if you really want to characterize relationship between two variables, you need to first estimate the beta naught and the beta 1. I gave you formula, okay, to do that. Because they have formula, we refer to them as estimator. I'm going to say that again, because the beta naught cap as a formula, the beta 1 cap as a formula, of course, we refer to them as an estimator. What is an estimator? Estimator is a method, a formula, or a formula that you use in estimating your parameters. That's what we mean by estimator. And you know what? For the estimator to be good, for your formula to be good, do you know that your formula actually, also rely on the absorption? Okay, and that was why I said assumptions of linear regression affect the properties of the estimators of the beta naught and the beta 1. And that is the reason why, if you want to estimate the beta 1 and the beta naught, you got to use a method that can actually lead to the drastic reduction in error. And that was why I call that method least square, because the least square will actually ensure, the least square that we use in estimating the parameters, the beta naught and the beta 1, will ensure that the unexplained variation is very, very small. Unexplained variation is actually the stochastic component of the linear regression model. It is also called the random error, and of course, and that is also called unexplained variation. We don't want our unexplained variation to be much. We want a situation whereby the explained variation will be much and the unexplained variation will be very, very small. Okay, whether they're going to be small, that actually depends on whether assumptions are violated or not. Now, oh my God, I've grouped this assumption into 4: linearity, independence, normality, equal variance. All these assumptions actually lies, or actually revolve around error. Now let me start with the assumption number 1: linearity. What do I mean by linearity? Linearity actually means, number 1, we expect a linear relationship between the two variables. Can you guys confirm if you guys are still hearing me clearly?
Gotcha.
Okay, good job. Now, the assumption is that linear relationship exists between the two variables. Okay, right now I'm trying to look at the relationship between the percentage of voters that voted for Republican candidate in 2012 and in 2016. The assumption here is that a linear relationship must exist before I can actually pursue linear regression, and we have a way to investigate Okay, we have a way to investigate this, which I'm actually going to show you in the subsequent lecture. But you know what? Mathematically speaking, we're going to say on our expected value of error equal to 0. Oh my God, what do I mean by that? What do I mean by expected value of error equal to 0? Now, in the context of, this example, where we're trying to characterize relationship between the percentage of votes received in 2012 and 2016, okay, by Republican candidates. What we're trying to say here, for the expected value of error to be equal to 0, it means on average. I don't want us to speak in mathematical time right now. I don't want us to speak in statistical time right now, but I want us to speak in practical terms. Now, take a look at me now. I want to speak in practical terms. If I ask you, what is the meaning of expected value of error equal to 0? Expected value of error equal to 0 means on average, every other factor that could affect, the percentage of votes received by Republican candidates in 2016, other than other than the variable we're considering. What was the predictor variable we're considering? The predictor variable we're considering is the percentage of votes received by Republican candidates in 2012. Okay, now, if because we believe there exists other potential factors that could determine the percentage of votes received by Republican candidates in 2016, other than what they received in 2012. Now, all those factors, their effect on average is 0. That's what we're trying to talk about right here. I'm going to say that again. When you have a linear regression model, particularly the simple linear regression model, where you are looking at the effect of X on Y, there are other potential factors that you don't consider. And what is the reason why you don't consider them? What is the reason why you don't include them in your model? You don't include them in your model because you are assuming that their effect is negligible. That is what this guy is saying right here. Their effect is minute. Look at that, minute. Their effect is minute or negligible, whichever way you want to use the English. Negligible, very small. That is what we mean. Or in another word, you're going to say they may be insignificant. Why do I need to include them? Because they could be insignificant. And so this is what this guy is saying right here. Okay, that's what we mean by linearity. Okay, we talk about independence right now. What do we mean? The dependence right now is just trying to say, okay, error from one county to the other should be independent. Okay, error in NP County should be independent from error in Anoka County. It should be independent from every county that voted in the election. That's what we mean by independence. Okay, we got a way to investigate this in the research. Now, the next thing that we're actually going to talk about is that the probability distribution of the error must be normal. Okay, because it is only when the probability distribution of the error is normal that the error can be well behaved. Oh my God, when we say well behaved, what do we mean by the error being well behaved? Error being well behaved means its effect is minute, its effect is very, very small. Okay, so we have a way to show, okay, whether the error in a simple linear regression model are normally distributed or not. Okay, and lastly, in the assumption, each error across county, based on the example we're treating right now, must have equal variance. Another name for that is what we call homoscedasticity. Oh my God, homoscedasticity. Homo means the constant variance. But you know what? If you combine all these assumptions together, okay, we can combine this, this guy here can be used to combine all the assumptions together. Now look at what I'm going to say right now. Error I follows a normal distribution with mean 0 and variance sigma square. This guy here is actually talking about this guy here. it means the mean of the error is 0, the variance of the error is sigma squared, and of course n here means it is normal, and EI, they are independently and normally distributed with mean 0 and variance sigma squared. We're combining all the assumption here in with just one equation. Take a look at that. Now, you know what? All these assumptions need to be met before we can actually use our regression model in policy formulation. At times it's going to look as if our models are failing us. Our models are not failing us, but we're not doing the right thing. Okay, do we bother to investigate whether assumptions underlying our models are violated or not? Most of the time, we normally jump to conclusion. We don't investigate. And that would be dangerous if you don't do that. So what I'm trying to show you right now, they are the conditions underlying the simple linear regression model. In the subsequent lecture, I'm actually going to walk you through how you can investigate. Okay, let me tell you, we got two ways to investigate this. We can investigate by graphs. Okay, then I'm actually going to be walking you through in the subsequent lecture. And we have a standard test that we can conduct to investigate each of these assumptions. Okay, now, like I said, the entire table can be summarized to be that. Okay, now I'm going to say that again. IID is talking about independence. N is talking about normality. Okay, then 0 here is talking about linearity, that expected value of error equal to 0. And sigma square here is talking about equal variance. Okay, so take a look at that. The entire table can actually be summarized as that equation. Okay, good job.
Excuse
Okay,
me.
okay, has a question?
Yeah, will you like repeat what that like everything stands for in that formula again? Like,
Okay, okay. Now, if I hear you clearly, you want me to repeat what everything stands for in the formula again, right?
yep, yeah.
Okay, thank you so much. Now, take a look at this guy here. This is the error I. Now, error I that has to do with a county. Okay, now when we say error high, what do we mean by that? The error high, the error is the difference between the observed, okay, and the actual. I'm going to say that again. The error high is the difference between the observed. Okay, what is the observed and what is the difference between the observed and the actual? What happened in reality, and of course, the estimate of the error is what we call residual. And what do we mean by residual? Okay, residual is the difference between the observed and the predicted. Of course, you're actually going to use your model to predict, right? What is the difference between what your model actually predicted and what happened in reality? Okay, so that's what we mean by residual. And the assumption here is that, take a look at this error high residual from any of the county. Okay, I'm just saying, okay, county high in the United States of America is identically, look at IID means identically and independently distributed. Let me write that. Identically and independently distributed. Okay, identically and independently and normally. Look at that. N means I'm talking about normal. Here I talk about normality, right, of the residual, which means zero. Means zero. That's I'm talking about that. Mean the expected value of error equal to 0, and variance sigma squared, which I'm talking about the equal variance. Take a look at that. When you define something like this, what happened here? This is the mean. This is the variance. Now, mean of what? The mean of the error. The variance of what? The variance of the error. So the mean of the error is the same thing as this. Expected value of error means the mean of the error. Does that make sense to you right now, the guy that has the question?
Yeah, yeah, thank you.
Okay. Okay. I'm so excited you understand that. Okay. Now, do you know that all this, somebody will say election has consequence, right? Election has also assumptions has consequences as well. And that is what I want to talk about right now. You remember the other time I asked you a question: what is y given x? You remember I said that? I'm going to take you back. I'm going to take you back. You know, there's a difference between expected value of y given x and y given x. Did you remember I said something like this? The one I circle right now? Okay, I want to walk you through that right now. Okay, there's a difference between this guy and this guy here. This guy here is just what is the expected value of y given that x equal to 50. That's a conditional mean. Okay, if I want to figure out what is y given x equal to 50, then I need the probability distribution for that. Okay, now I'm going to walk you through that. Now you're going to see, why are we doing this? Assumptions as implication. Now take a look at that. What is the implication of linearity assumption? What is implication on what? What is implication of linear regression assumption on y given x? Of course, the implication is that if expected value of ei equal to 0, then the expected value of yi given xi equal to xi will be equal to the model. That's what we mean. Okay, that is the implication for linearity. Look at that. The implication of linearity assumption on y given x. Now, the implication for independence, okay, the implication of independence is that on y given x is that y given x in any county, okay, that's what I'm trying to say, y high given xi, okay, will be equal to xi. That is implication. I want you to take note of that. Now, what is implication of normality? Okay, that is implication of normality. What is implication on the constant variance? That is implication. Now, let me tell you this. If errors are independent, the implication is that yi given xi equal to that will also be independent. I'm going to say that again. If errors are independent, okay, because we expect the prediction from every county to be independent. Let me tell you this. In the recently concluded presidential election in the United States of America, okay, Trump campaign actually alleged the other party of electoral fraud. There is possibility that there could be electoral fraud or not. And I could remember in December, uh, the state of Texas. I don't know whether you guys are aware of that. For those of you who are following the political spectrum in the United States of America, the state of Texas actually took some states that I call the battleground states in this recently concluded election to Supreme Court. Okay, and what the argument of Texas was that uh, the other states violated their constitution in the conduct of the presidential election. But do you know the verdict given? Uh, the interpretation of the verdict given by the Supreme Court is that Texas does not have any right to decide on the election of another state. Every state in the United States have their electoral law. Now, we take a look at independence right now. Independent means if I want to predict, okay, an election result from a particular county, it should be independent of another county. I don't know whether you guys are getting my interpretation right now, and that's what we mean by independent. If errors from across county are independent, the implication is that whatever we want to predict from any given county should be independent as well. That's what we mean. Okay, the prediction from this county shouldn't exactly. Somebody says so. The decision of one county is not affected. That is what I mean. Let me read your chart. It's unaffected by decision of another. Yeah, because every county is independent. That is the assumption. Every state is independent. You get what I mean? So that is what we mean by that. And you know what? When the errors across county are normal, then the implication is that whatever prediction you want to make, Okay, y given x equal to that will also be normal, because we are expecting them to be normal, and the only condition for them to be normal is that the error has to be normal. Okay, and you know what, another thing is that the implication of the constant variance is also that this guy here is also going to have a constant variance. Okay, it means the variance, as there's always going to be variance associated with prediction from a particular country. And you know what, the moment the error across country has equal variance, then yi given xi equal to small xi will also have equal variance. Okay, so this is implication. Okay, and let me tell you this: if these are not met, it's actually going to be an exercise in futility. It's going to be an exercise in futility. Now, if I now want to ask a question about the distribution of y, look at that. That's what we're seeking to know, because we know from county to county, this is a random variable because it varies. Okay, because it varies. Okay, from county to county. Therefore, if anything varies, if a variable, if something varies, then it means it's actually going to have a distribution, a probability distribution. Okay, now take a look at this. Oh my God, this is what we're going to have right now. The distribution of y, given that x equal to x, follows a normal distribution. What is the mean? Oh my God, this is the mean. What do I call the mean right now? This is expected value of y given x equal to what? Beta naught plus beta 1x. That's what I call the mean. The mean of what? The mean of y given x equal to that. On average. That's what we're trying to talk about. Okay, and that mean represents the deterministic part of a linear regression model. I'm going to say that again. That mean represents the deterministic part of a linear regression model. Okay, because before we can actually have this to be the mean, then it means on average we're trying to say expected value of error equal to 0. That's what we mean. And that is why we can have this to be the mean for that, because we have an assumption that the expected value of error equal to 0. Now take a look at this right here, sigma squared. So which means the variance of y given, give me 1 second, given that given that big S equal to small s is actually equal to sigma squared. And don't forget the variance of EI is also sigma squared. So which means the variance of error in a linear regression model is the same as the variance of y given that x equal to small x. They are the same. That is implication. And that's what we expect. We expect them to have the same variance, constant variance. But you know what? They get a different mean. Don't forget, the mean of the error is 0, but the mean of y given x equal to x is the beta naught plus beta 1s, which is the deterministic part of the linear regression model. Therefore, what conclusion can we make about the distribution of y given that big S equal to small s is actually going to be normal? This is what we mean by normal. Look at that big N, and it has a have conditional independence, okay, and have equal variance as well. Take a look at that. So that is the conclusion that we can actually make. And of course, the diagram that I'm trying to show you right now is just to indicate that if this is my mean, the deterministic part, expected value of y, okay? Now, if you take a look at this guy here, this is the expected value of the response given predictor x. But this guy here, okay, if y equal to 108, okay, if you take a look at what I have there, this is shift to the right. Look at that. There's a shift from 25 to 45. Look at that. Okay. And when you take a look at this, expected value of y equal to 104. Okay. The y equal to 108. Y 108, probably that is a actual value. Actual. Y 104 is more or less like a predicted, and the average value. Now, what is the difference between 108 and 104? Is actually 4, which means 4 is the error. Okay. which means 4, is actually the error. Take a look at that. Okay, now I want to quickly go back to our example. The examples on the Trump, or uh okay. Now looking at this example right now, we've been able to develop a model based on counties in the United States of America, except the one in Alaska. And we believe that if 50% from a county voted for a Republican candidate in 2012, 53.924% is expected to vote for Trump. Okay, I think I showed you this uh, the other time. But the next thing I want to talk about right now, do you know that if I take a sample from counties in the United States of America, maybe for instance, I work on 10 county. I take that randomly. Okay. If I compute my beta naught and beta one, it's actually going to be different from the one I got when I use all county. And that is what I want to showcase right now, that we call the sampling distribution of least square estimators. Okay. But before I'm actually going to explain that, now let me tell you what I want to do now. What I want to do now is just that to tell you that if I take a sample size, okay, if I take a sample size of 10 county, okay, and I compute my beta naught and beta one, the value that I'm actually going to have will be different from when I use all county. And if I go into population several times to take a sample, if I compute my beta naught and beta one, they're going to vary from sample to sample. I'm going to say that again. If I go into population and I choose a sample size and I compute my beta naught and beta 1, the values of beta naught and beta 1 is actually going to vary from sample to sample. And when they vary from sample to sample, it means beta naught and beta 1 now become random variable. Then we need to be able for us to be able to know the true value. What is the true value of beta naught? What is the true value of beta 1? We need to be able to investigate what is the probability distribution of the estimators, the probability distribution of the beta naught and of the beta 1, because if I know the probability distribution of beta naught and beta 1, I will be able to use the knowledge of that to figure out the average of the beta naught, because I'm going to have so many beta naught, so many beta 1, and that is what I want to showcase right now. Okay, now I want to give you an example. We have a parameter mu. We're looking for average in a population. Okay, and we cannot study the entire element in the population. We're going to take a sample. When you take a sample and you want to find the mean, this is the formula you're going to use. Therefore, this formula is an estimator. Okay, I want to differentiate between parameter, estimator, and estimate, because you need the knowledge of that to be able to understand what I want to explain in the linear regression. Because we also have parameters in linear regression, beta naught and beta 1. But right now, what is the difference between this is a parameter, this is an estimator? 5, the value that I got. Where did I get this formula from? I mean, this value from the value that I got from this formula. That's what we call estimate. There's a difference between parameter, estimator, and estimate. Parameter is what we're looking for. It's a population characteristic value that we're looking for. We're looking for the mean. We're looking for the average of something, okay? And that is symbolically represented by mu. But you know what? We're actually going to take a sample, because we don't normally study entire elements in the population. Then if I want to find a sample mean, I'm actually going to make use of this formula here. The formula here is what we call estimator. Okay, now the particular value that I got using the formula, maybe I may got 5 or whatever. That's what we mean by estimate. Now, if I now want to extend this to linear regression, what are the parameters in the linear regression? Oh my God, parameters in the linear regressions are beta naught and beta 1. Look at them. Those are parameters. Now, what are the estimators? Oh my God, look at the estimators. These are estimators right here. I want you to see the difference between estimators and parameters. The parameters will not have a cap on them. Can you see? Beta 1, beta naught, no cap on them. But look at the estimators. Look at that. that has a cap. Okay, but you know what? Uh,